Welcome to Keentel Engineering Large Load Interconnection for AI Data Centers. This presentation covers the full interconnection engineering stack, power system modeling, EMT studies, performance requirements, and the interconnection process itself. AI data centers are connecting to the grid at a scale and speed it was never designed for. The engineering has to catch up. Let's get into it. The scale has changed. Single campuses now exceed 1 gigawatt, a load the grid was never designed to serve. Three things make this uniquely difficult. GPU workloads ramp in seconds, not minutes. Conventional load models don't see that. Protection logic can trip gigawatts simultaneously in a coordinated event, not gradually, all at once. And 20 years of flat load growth ended abruptly. The planning assumptions built into every transmission model in the country no longer apply. Legacy composite load models miss four things that matter for AI data centers: cyclic variability, ride-through logic, harmonics, and phase jump thresholds. The modeling approach has two tiers: positive sequence first, bulk system impact, voltage stability, frequency response, inter-area oscillations. Use it for every facility. Then EMT when screening triggers fire, PLL instability, subsynchronous oscillations, converter interactions. 6 criteria determine when EMT is required. The rule is simple. Start with positive sequence, add EMT when the screening flags it. Use both. 6 conditions trigger an EMT study requirement. 1. Facility exceeds 100 to 200 megawatts, depending on system strength at the point of interconnection. 2. Low short-circuit ratio. Weak grid means PLL stability risk. 3. Sited near inverter-based generation. Power electronics to power electronics interactions can destabilize both. 4. High-frequency load cycling above 0.1 Hz, which can excite inter-area modes. 5. Interconnection at 230 kilovolts or below, where local systems are more susceptible to fast transients. 6. Electrically close to generators, requiring torsional interaction screening. Any one of these triggers EMT. Most large AI campuses trigger several. There's a fundamental conflict baked into every large load interconnection. The grid operator's requirement: stay connected, remain electrically tied to the transmission system, and restore load on specified timelines. The facility operator's requirement: keep computing. Internal processes continue on UPS while simultaneously disconnecting from the grid to protect equipment. ITIC curves protect equipment, they do not protect grid connectivity. These two objectives are not the same, and they are frequently in direct conflict. Interconnection agreements must specify grid-oriented ride-through curves explicitly. ITIC alone is not sufficient. Multi-strike disconnect logic is a specific underappreciated risk. A double circuit fault followed by an unsuccessful reclose is a designed-for routine grid event, but it can trigger counter-based disconnection logic inside data center facilities, removing gigawatts from the system simultaneously. The preferred approach: disable multi-strike logic entirely. If it's technically feasible, make that a condition of the interconnection agreement. If it can't be disabled, the counter thresholds must be coordinated against all designed-for contingencies, including double circuit faults and unsuccessful reclose sequences. This is not a theoretical edge case. It has happened. The right interconnection process follows 7 stages: pre-application readiness, application and model package submission, Tier 1 RMS positive sequence studies, Tier 2 EMT studies when triggered, interconnection agreement execution, construction and commissioning, and post-interconnection monitoring, which most projects skip and shouldn't. The parallel here is generation interconnection. That process took 2 decades to evolve from fragmented utility procedures into enforceable standardized frameworks driven by the reliability failures that happened when it couldn't keep pace. Large load interconnection is in the same early period of that same evolution right now. One real project: 600 megawatt hyperscale AI campus, 345 kilovolts, high inverter-based resource region, multi-OEM GPU procurement, known subsynchronous oscillation risk area, 5 models developed. 3 positive sequence, 2 EMT, dominant oscillation amplitude reduced by 75%, multi-strike counter threshold revised from 5 strikes in 30 seconds to 12 strikes in 60 seconds. Interconnection agreement executed with monitoring requirements embedded. The key insight: 0.3 Hz AI training cycles were aligning with the regional inter-area oscillation mode. Mitigation was rack-level BESS buffering combined with job scheduling smoothing. 2 engineering solutions working together. 3 engagements, 3 distinct lessons. First, the 600 megawatt AI campus at 345 kilovolts. Cyclic 0.3 Hz load aligned with the inter-area mode. 5 models, 75% oscillation reduction, counter threshold revised. Second, a regional utility managing an 8 gigawatt interconnection queue. Commercial readiness filters cleared the speculative applications. 31% of megawatts withdrew. Study completion time dropped 28%. Mitigation was found in 2 of 14 remaining projects. Third, a 400 megawatt electrolyzer at a short circuit ratio of 2.8, a genuinely weak grid. Standard IBR ride-through rules didn't apply, partial load reduction to 40%, 4-stage voltage-gated recovery over 60 seconds, and a 60% reduction in membrane thermal cycling stress. Weak grid requires tailored curves. There is no standard template. The large load era is an engineering challenge that can be met. The tools exist: dynamic model development and validation in both positive sequence and EMT, forced oscillation and torsional interaction studies, site-specific ride-through and performance requirements, and interconnection process framework design. 3 things make the difference: accurate models, clear requirements, and structured processes. If you're navigating a large load interconnection, as a developer, utility, or regulator, reach out to Keentel Engineering at keentelengineering.com.